In this example, I want to consider also in another similar homework problem, the effect of multiple pulleys on a system. And so what I want to do is have pretty much a heavy block, kind of like this, big M. And let's say it's connected to a pulley attached to a wall. And then other side, there's another pulley for which there's a hanging mass. So hopefully the picture makes sense. Yeah, it is set up that way. For now, we can ignore the role of friction. But what's the acceleration? I mean, how do you analyze the system? What's going to happen? The thing is that in this example, the accelerations are different. The acceleration constraint is actually something that's the most confusing, because if you look at the string has a fixed length. So when block M, little m, has gone down by a distance of d, block big M, it might take some thought to convince yourself, has only moved by a distance d over 2. That's because the rope, this part of the rope that moves a distance d, only half of it wraps around the pulley when M goes down the full distance. And so that's going to change the accelerations. And so maybe instead of big M and little m, let's make this 1, and let's make this 2. It makes the acceleration constraint a little cleaner. Okay, because M1 is supposed to be kind of a heavy load, a big load, and M is a kind of a counterweight. So what is this acceleration constraint going to be? This is the confusing part. We'll have a sub 1x equals half. It'll be minus 1/2 a sub 2y. That's the confusing acceleration constraint. After that, the free body diagrams are pretty straightforward, I think. The bottom M has a T upward, and then M1G downward, and F net downward. 1. We're using the obvious coordinate system. But what's the free body diagram for M, for the big mass? That'll be, I'll just draw it way down below. That'll be, it's a M, oops, I have the wrong, numbers, don't I? This should be 2. It should be 2. So the free body diagram for the hanging one, or the fixed one, is M1G down, N1 up. But the tricky thing about the pulley is that there's actually 2 tensions of the same size. And that contributes to F net of 1. So I'm not using a coordinate system. I mean, it's an obvious one. So it takes some convincing to show that when it's attached to the pulley, it feels 2 tensions, but that's always what the pulley feels. The pulley always feels 2 tensions. And so if I sum the forces, I'm going to have 3 equations, not nearly as difficult as some of the other examples, but you're going to have 1x, 1y, which that one doesn't matter, and then 2y. So 1y is the obvious n1 minus m1g equals 0, the one that we don't use. 1x is going to be 2t equals plus m1a, and then 2y, the one that's hanging, it'll be the same t minus m2g, this is where the acceleration constraint comes in, equals minus m2 acceleration over 2. So that's how the acceleration constraint shows up in this example. You have to be careful how you're defining A, because in this constraint, it looks like we define this to be A. Let's see. Which actually means, and this is my fault, that the first one should be over 2, and this Yeah, this bottom one should be X'd out. This is something that's really tricky about the constraint. You got to make sure that MA or MA over 2 is correct. So we find this is 1. It's half of, right. Okay. Right. And so solving these two equations will be an exercise in making sure these 2's get to the right spots and don't get messed up. I believe this is a similar example of a homework question that you have where the pulley is instead on the bottom one, like the wall is on the top, something like this, and the box on the wall. And the pulley is attached to the hanging block. This is a different one. It's about the same geometry, but the fact that the moving pulley is on the hanging block will affect the accelerations. Now, the accelerations are flipped. If this is A, this one is A over 2. So you got to make sure to resolve those A's and A's over 2's to work with those. But these are really fun examples, and it might seem like you're getting something for free, but it's really the concept of leverage and sort of mechanical advantage that shows up in these problems. So these are two simple examples of multiple pulleys, and we won't really get into examples that are any more complicated than that. Sometimes folks in like an engineering class in high school may have seen stuff like this, but it varies. So mechanical engineering folks might actually see stuff like this later on.